Great. Welcome, everybody from all over.
Welcome, welcome, welcome. Welcome again, everyone, to the January 2024 NASA Night Sky Network webinar. We are hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. And we are very excited to kick off the year with our guest speaker, Dr. Miguel Fernández, with his talk, Finding Aliens on Earth. For our Zoom attendees, please be sure to use the chat to say hello and use the Q&A window for any questions. Please don't put your questions inside the main chat so we can see them and we'll be able to answer them near the end of the webinar. And before we go into Miguel's full introduction, here's Vivian White with some announcements.
Welcome, everybody. It's a huge crowd this evening. It's nice to see you all out. I just want to let you know that this evening we're going to be speaking with Dr. Miguel Fernández, and then I want to make sure that the club coordinators from all the Night Sky Network clubs know that January 31st is the final date to request more than 3 pins. If you don't know about this, go ahead and check your email. You should have a great email from 2 weeks ago that tells you all about it from nightskyinfo@astrosociety.org. I'll stick that in the chat. Also, February 4th is the last day to request NASA speakers. Make sure that you become an active club. If you are not already, check with the rest of your club coordinators and make sure that that's happening. Active clubs can request NASA speakers as well as get these beautiful pins that Kat designed. The moon moves by design. It's an eclipse, just so you get all ready for the eclipse. Let's see what else. We've got some office hours. I'll stick that link in the chat right now. And the eclipse ambassadors, if you would like to get ready for the eclipse, whether you are on or off the path, this is something to get your communities ready before the eclipse comes. So I'll stick those links in the chat too. We welcome everyone to join us. We're going to prepare all of the communities off the path because we know that many of us, if we are lucky, are going to try to get to the path of totality on April 8th. So let's get our communities ready while we're gone. And I think that's it. Anything else, Kat, that I missed?
Not that I can think of, but yes, the moon does move by design. And like Vivian said, get your events on the calendar. You only need 5 for the year or 2 for the quarter. So please, 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 if you have meetings where it's just your club meeting for regular business as usual, if you have community events, go ahead and put them on the calendar for 2024.
I forgot one more thing.
Oh.
If your club has at least 10 events posted for 2024 on the calendar, you'll get extra eclipse glasses in your eclipse package. So keep an eye out for that. I'm putting in the chat about how to schedule recurring events. It's a very simple process, and you can get all your club meetings up there, and then you'll get extra eclipse glasses. We're excited to send those out, and you'll hear more from us soon.
Excellent. All right. So again, welcome to the January 2024 webinar. And tonight's guest is Miguel Fernández. He is a microbial ecologist specializing in extremophiles, astrobiology, and instrumentation development. He is currently working on as a postdoctoral fellow for the María Zambrano Excellence Program at Universidad Autónoma de Madrid, where he is conducting studies focused on Antarctic lakes, Atacama Desert soils, Iberian temporary salty lakes, and Rio Tinto River sediments. Previously, he worked at Centro de Astrobiología in Spain and at McGill University in Montreal, carrying out similar research along with the development of space exploratory instruments such as SOLID, which is Signs of Life Detector, and CAB and MicroLife detection platform at McGill University. So please, everyone, welcome Dr. Fernández.
Hello, everyone. Hope you can hear me loud and clear. First of all, I want to apologize for some things while I'm trying to start sharing my screen. Okay, here I have the chat. Where's my screen? Here. Yeah, first of all, I want to apologize for my language skills, which I know that I'm not a native English speaker, but I will try my best. And after that, I will try to do this presentation interesting for you. But I will also want to apologize because it's quite late here in Madrid. I'm based in Madrid right now, so I'm probably look a bit tired, or maybe I will look a bit sleepy. I'll try to make it as good as I can. And after that, I hope that we don't have another problem, technical problem, as a technical problem that Kat mentioned just a minute ago was from my side. Apparently, my Wi-Fi didn't work for a while. We were all scared that I'm not going to be in time for the meeting, but apparently it works now. So fingers crossed. Okay, yeah. Yes, as also Kat said, I'm currently working at the Universidad Autónoma de Madrid here in Madrid. Here you can see all the, let me put my laser in here. Yeah, so here are all the institutions that I belong to. Universidad Autónoma de Madrid, as I said. This is the Center for Climate Change and Biodiversity Studies. This is my lab, Microbial Ecology Lab. And I'm also part of some associations. One, as you can see here, APEX, that is Association of Polar Early Career Scientists, and one that you may want to check out. It's Alpha Mars. It's Agnostic Life Finding Association Mars. It started year and a half ago, but we are looking for new members, so please check it, and you will be welcome. And also, I want to say that you will be able to find me in social media. You can find a nice profile with nice videos and nice pictures from Antarctica and all other places that I am going to show you now during my webinar. In X, also formerly known as Twitter. I will always say Twitter. I'm sorry, Elon Musk, if you're listening. And then you can check me out in YouTube, where I have some videos. Unfortunately, they're in Spanish, so well, fortunately or fortunately, because you can just try to improve your level of Spanish language. So, well, my chat is my presentation will be about Finding Aliens on Earth. That's a nice title. I was trying to show what I do. Here you can see an image that represents me. Actually not, but someone that looks like me, a scientist in his bench, and looking at different places on Earth, a desert, a polar area, cave, or something submarine, and a river. And the subtitle is "What Extremophilic Microorganism Can Teach Us About Life in the Solar System." So before starting, I want to, as also Kat said, tell you where I come from. After finishing my PhD, I started working as a postdoc in the Centro de Astrobiología. Sorry, was mixing Spanish and English, you know. What means Astrobiology Center in Spain is here in Madrid. Is a very nice place. It's a very good research center. I don't know if you have ever heard about it, but some people from there, some engineers, has 2 or 3, I don't remember at the moment, 2 or 3 instruments on Mars. MEDA instrument, REMS instrument, very big science is done there. It's a very unique center because it mixed all the astrobiological people working together. It means people from the biology side of the problem, as me, people who are chemists, people who are astrophysicists, people who are engineers. It's a very nice and very unique place, at least in Europe. You don't find this in the same building, in the same center. You can find different institutions or different departments in different universities that works together, but having them in the same place, working all at once, is very unique. And after that, I was working there from 2017 and 2019. I moved to Montreal 2019, just before the pandemic started. I don't know if you remember that pandemic. We had that some years ago. And I moved to McGill University. I worked for, let's say, 2 years and a half in this lab. This is a wide lab. It's a polar microbiology and astrobiology lab. And I was also part of the MSI, which is the McGill Space Institute. And working in these 2 places, I had the opportunity to work together with people from ESA, from ESA, from NASA, and it's obviously when I was working in McGill University with the Canadian Space Agency. So what I wanted to show with this slide is just I moved a bit from my place, and it's great to be here talking to you in the States. I have been reading the chat before starting my webinar, and I saw that you are all along the States. That's really nice to have you here listening to me. And well, let's get into the talk itself. So I wanted to show you this next slide because I have been checking what webinars have you been having in this really nice association that you have, the Night Sky Network. What I have seen, correct me if I'm wrong, but most of the talk that you already had here were about astronomy. Most of you, or I don't know if all of you, are astronomers, so or astrophysicists or physicists. So this slide shows that for this time, with my talk, we are moving from the telescope to the microscope. We are moving from astronomy to astrobiology. I don't know if you have ever heard about astrobiology. So here I have a definition of what it really means. Astrobiology is a science that is a mixture of different sciences. But if you are looking for a definition of it, probably it will be the study of the origin, evolution, distribution, and future of life in the universe. Seems to be more or less easy to define what astrobiology is, but if you see carefully this slide, you will see that life is written in a different type, in a different style. Why? Because, well, it's easy to define what astrobiology is, but what if we have to define what life is? I tell my students it's really easy to say if something is alive or is not, but if you have to define life in a philosophical way, it gives you some problems. But what about if you try to define it in a scientific way? It's even more difficult. So if you try to search it, if you do a Google search on what life is, you will find a lot of definitions, but probably the one of the first ones that you will find is the NASA's one. This is life is a self-sustaining chemical system capable of Darwinian evolution. I mean, it's not very easy to understand this, even for a biologist like me. You see self-sustaining, you see chemical, you see different words. Darwinian evolution. Everybody knows about Darwin, but what about Darwinian evolution? So we use this as a frame for what we need to look for, what we need to study. You know, Darwinian evolution means that you can adapt without changing in one single organism, but during the lifetime of centuries, the organisms tends to change. And with Darwinian evolution, they will be selected just to be the most adapted to the environments that they are living in. Once we have the definition, I don't want to extend myself more in here. We have to think on, okay, we know what life is, how it is defined. We know if something is alive or not, but how these living organisms will look like. If we look at what we have on Earth, we will see something like this. This is a representation, an artistic representation, but this artist, Giulia Ghiselni, it's Italian, I think, which shows in a really nice way, as I said, the tree of life. It's a different representation of the tree of life. Here in the center, you have Luca, which is not Luka Doncic from Dallas Mavericks. I'm sorry if someone is from Dallas in here, but it's the last unique common ancestor of all the organisms that are actually living on Earth, currently living on Earth. So if we see at this graph, we will see that from here to here, let's say 3/4 of the circle. If you are talking about abundances, it will be much more. Well, all this part of the organisms that are shown in here are microbial organisms. You cannot see them without a microscope. We're getting back to the microscope, leaving the telescope for today. And just this part of the circle where we are is something that you can see with your bare eyes. For the rest, you need a microscope. So if we are looking for something that is live outside Earth, probably it will look like more like this than this. All the time in movies, in cartoons, in comic books, everywhere you will see aliens, especially Martian people, that will look like green people with big eyes, big heads. But if we try to look at, or we try to think about what life will look like from a scientific point of view, you will have to think more on this. You will have to look more on, you will have to think more on microbes. Different colors, different shapes, different metabolisms, whatever, but probably microbes. So now that we have the idea of what life is, how it will look like, you start to think about different other questions. Probably you will start wondering, as you have me here, just looking at our marvelous Milky Way, but asking myself questions about what life in the universe is. For example, there was only one single origin for life, the one that happens on Earth, or there was different origins in different celestial bodies in the solar system or other places in the universe, or even was different there was different origins for life even on Earth, and just one just thrived through the history until the days that we are living now. Maybe you can ask yourself, maybe you can wonder, if so, if there were more or, well, only one origin of life, is there life in any other place in the universe? Are we alone? That's the big question in astrobiology, right? And if so, if life appeared in a different place in the universe and is there now, are we going to be able to detect it? Because, well, it may look like the life that we have here on Earth, but it may not. So we have to be ready for that. Let's try to answer all these questions through the talk that we have today. Trying to answer the first one. Here you have something that you really know much better than me. I don't want to extend myself in here, but if we bear in mind the Big Bang theory, we know that all the universe started from the same place. It started with creating the lighter elements until we get to our time. I don't want to stand it here because I probably will make mistakes, and you just know this. But after the Big Bang, until we get to our days, where all the heavy elements were formed, and because of that, we had the different planets, different moons, different matter in the universe. All the elements that forms this part in here, including living organisms that we know that they are on Earth, are formed by the same elements. And from these elements, we just need 6, as you have here in the right, to form living organisms. You start with hydrogen and carbon. To form the hydrocarbons, you can add oxygen to it to create the lipids as well as the carbohydrates, sorry. Then if you add nitrogen and sulfur, you will have different amino acids and proteins. And finally, if you add the phosphorus, you will have nucleic acids like RNA and DNA, things that the biomolecules that have all the information, the genetic information in all the living organisms that we know so far. So with only these 6, they are called CHOMPs, because you usually use the carbon before the oxygen. You will have life. That's the only thing that you need for having life. So trying to answer the first question, there was one only single origin for life. Maybe it was, but it could be a different thing. It could have happened many times in the universe and during the history, because of the elements that we have all around, widespread in the universe. All of these just need to be combined. Actually, if we look at a paper that was published 2 years ago, they found this component, ethanolamine, that it's a basic component, here you have it, of the cell membranes as the cells that we have here on Earth. It was found on the atmosphere of Venus, on the clouds of Venus. The ethanolamine was found there. So if it could happen because we have these same elements all around the universe and they just need to combine, and now we have found that there's one of the basic elements that forms the cell membranes, they are present. You can find it on Venus clouds. Why is not going to be in a different place on Earth? why don't life has been created, has been occurred somewhere else on Earth, on the universe, instead of only on Earth? If we had this idea in mind, then we have to think, okay, there could have been one only origin for life on Earth, but what about life thriving on different, I was said on Earth again, sorry, on the universe. What about if, what we need to have life thriving? What do we need to have life developing on Earth, on the universe? We need some kind of environments that allows these living organisms to reproduce themselves, to grow, to metabolize with the elements that we have there. So here we have a second question. Well, that's the answer to the second question. It's it needs to introduce another term that is called habitability. So if there's life anywhere else in the universe, it's going to be present anywhere else. I mean, if the origin has been in different places, is what we need to have it in different places. So here is habitability, and here is the definition of it. Something that we really need. It's a condition for life to thrive. So we need to have habitable places. What's habitability? Here you have it again. The measure of a planet's or a natural satellite potential to develop and maintain environment hospitable to life. So we need to have life. We need to have life created, and then we need somewhere for this life to thrive. It means here on Earth we have a lot of habitable environment, but what about in the rest of the solar system, for example? Let's reduce our scope to the solar system only. And well, here you have an example. What means to be habitable? For example, for a teenager, probably it will mean having a good Wi-Fi connection. Even not for a teenager, even for a scientist from Spain trying to connect to the Night Sky Network webinar this night, and not having it is a really big problem. So Wi-Fi connection would be a condition for habitability, and we have it. We know that we have it on Earth, but what about in our neighbors like Mars or Venus? We don't have that. Well, actually, this is a joke, and what we need to be is first of all in the habitable zone of a star. If we're talking about the solar system, probably we can just assume that this represents Earth. We need to have a decent side of planet. Then we will have another planets that are close to us, but in a place that is too hot for life to develop, like Venus. You know that Venus presents more than 400 Celsius degrees in its atmosphere. Or we may have something that is farther from the star, like it could be, in this case, it could be Mars. Okay, it's too big to be Mars, but well, you know what I mean. So Mars is too far from the sun to be warm enough. It could be too cold. And actually that's what happened to Mars. So after being in the right place in the solar system that we are talking about, let's talk about our solar system in this case, you need to have some elements, basic elements, apart from the atoms that I mentioned before. You need to have this. This is an example of a single habitable cell, a single habitable environment. What it needs to have. So this is extracted from Charles Cookell paper from 2021, where they describe different units for habitability. And this is the most simple one. You need a gaseous environment, let's say an atmosphere. Then you need water, liquid water, or some kind of water that acts as a matrix for chemical reactions. You need a solid state substrate. In this example, it's a rock, it's a basalt rock. And then you need the elements that I mentioned before, the atoms. You see the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and traces, small amounts of other compounds, as iron in this case. And then what you need is a source of energy. But the source of energy is just two elements that combine, two molecules that can combine together and move electrons from one to the other. Here it's represented from ammonia to oxidized iron in this case. So this will give the electrons to the oxidized iron that will become an reduced iron and a reduced nitrogen. So with this, only with these few elements, we can have an habitable environment. But, my friends, there's a big difference between being habitable and being inhabited. Actually, this is what happens on our neighbors. I'm going to focus on Mars because it's the planet that I know more about, and all my experiments have been related, not all, but most of them have been related to conditions on Mars. So if you have a quick look at it, here is a wonderful NASA video showing the surface of Mars. You will see that it looks bare. I mean, you cannot see any living organisms in there. You cannot see trees, you cannot see animals, as we all know. There's no life, macroscopic life on Mars, so far, as we know so far. And there's something that, apart of having all the elements from the list that I showed you before, the cell of habitability, there's all the elements but one, that it's liquid water, at least in these images. So we have a problem. We have all the elements. We have the electrons movement system with different elements. We have the TOMS elements. We have an atmosphere. We have a solid substrate as rocks that we have here, jarosite, basalt, also volcanic rocks. But we don't have liquid water. Has this been like this all the time before? Well, following what our friends in here, curiosity and perseverance and ingenuity. Well, ingenuity is not going to send us any more pictures, as I have read today, I think. Correct me after the talk in the chat if I am wrong, but I have read that it's not going to fly anymore. It sent us a lot of very nice pictures, so well done, ingenuity. And perseverance, well as curiosity, as I said, told us that there was liquid water before on Mars. There was a lot of environments that had liquid water in the past. We had some nice pictures, but we also have some analysis coming from all these missions, not only these two, showing that there are chemical proofs, chemical results that showed us that there was life. There was water on Mars. For example, in this video here, I'm showing using the Mars Trek tool from NASA, where all these minerals that you have here on the right are present on the surface of Mars, where we have detected them so far. So what's the cool thing about these minerals in here? Well, following what we know from those minerals on Earth, we need water to form these minerals. So if you have a quick look at this last image from the video, you will see that they are all widespread around the Martian globe. So if we need water to form them, and you can find them anywhere else, anywhere in the surface of Mars, it means that there was water on Mars. And that's really interesting. If we have a closer look to the Martian surface, we have something like this. Everyone that has gone to the field, to some clay area after a storm, will have seen something like this. This look like mud ponds. If you see here, like it happens on Earth. This is only an optical effect. I mean, Mars is totally dry, but the structures that you see on the surface are really similar to the ones that we have here on Earth after rains. What's important about this? Well, now we know that there's no liquid water on the surface of Mars, but we have the rest of the elements necessary to have an habitable place. So if in the past we have liquid water on the surface of Mars, does it mean that it was habitable sometime in the past? Well, why can we say no to that? So, well, here I want to show you also that we are always talking about liquid water, but we have found last week from ESA mission Mars Express, if I am not wrong, that here in the middle of the equator, there's this formation, the Medusa Fossae formation, and this mission, the orbiter, the Mars Express, has told us that there's some ice in the equator where the temperature seems to be higher than in the rest of the planet, like obviously in the poles where sun just goes very slightly, sun rays. And this is not something that is small. If you see the scale in here, you will see that in some parts, like this part in here, the thickness of the ice is more or less 3 kilometers, 3 kilometers thick of ice. So we have water ice in the middle of the country. So we know that there's no liquid water so far in the surface now, but we know that there's some ice, so water ice, and beneath, below the first centimeters of the surface. Here you have the proof. So what happened to the planet? Well, the first idea is that it happened something similar to this. It started with being a planet with oceans and rivers, and it started to lose their water, to lose its water from there, and it was related to some places on the poles. But if we now know that there is some ice in the equator, probably what happened is between this state in here and the last state where everything is dry, there happened something like this. So the oceans, before drying out, it became some ice on the surface. And probably what happened is that with the winds in the atmosphere and the regolith, this thin material that you have in the surface of Mars just cover these areas, this ice on the surface of Mars. So we have all the elements that are needed to have life in there. And if there was life while these two states were happening on Mars, I mean, when we have water on it or we have ice on it, if life was present there, how it may look like? Well, we don't know, but we have, again, our friend Perseverance here grabbing some samples for us. Let me drink a little bit of water. Okay, so what Perseverance is doing, and this is for me, from the perspective of an astrobiologist, the most interesting thing about this mission is that it is keeping samples from different places in the surface of Mars in tubes. And then with the Mars Sample Return mission, these tubes were thought to be taken back to Earth. I said were because, as far as I know, this mission has been delayed or defunded. You people from NASA can correct me and say what's the right term for this. But what it's real is that this mission is now stopped. So we're going to have these samples back on Earth, which will have meant that we'll have been able to study them with state-of-the-art techniques of live detection. So we have just to keep with the analysis that Perseverance is doing there, that are great, but they are not. Let's say they are not definitive to say if there was life there or not. So, well, this is just another picture just showing you how these samples look like after they were taken from the surface by Curiosity. What this leads me to is to the thing that, well, we can wait until we have these samples back on Earth, which we don't know when it's going to happen. We can also try to develop things like this, which will be perfect, like robots that allowed us to go to Mars and do our sampling and our analysis there on site without a big effort. I don't know if you have seen the film The Martian, well, something similar to that. Or else what we can do, and what I do, we can just look for environments that resemble the conditions that we have outside Earth. We're talking about Mars, but we can talk about any other place that is within the habitable zone, or even far from the habitable zone. I will show you some examples afterwards. Or we can, as I said, we can wait for this, or we can just go to places on Earth that resembles the conditions that we have on those places. And those places that we have on Earth that resembles Martian surface, and other places in our solar system, it's what we call the terrestrial analogs. Terrestrial analogs, here you have another definition, are places on Earth that, following one or more of their environmental parameters, resemble other solar system bodies. So if we have the conditions that are similar to the ones that we have in a different solar system bodies, and we know that these conditions probably were present anywhere else outside Earth, and we know that on Earth we have living organisms, why are not going to think that this same situation with living organisms has happened anywhere else outside Earth? That's the way of thinking in astrobiology. So talking about these environments, these terrestrial analogs, I want to show you some pictures and explain a little bit of what I have done and what my work is about. First of all, I want to take you back to this situation some million years ago, where Mars has all the ice in water ice in its surface. And if you think about this situation, it directly reminds you of the polar regions on Earth. So first of the polar regions on Earth that we can consider terrestrial analogs is the places in Antarctica. Here you see a nice picture of my first visit to Antarctica, where I studied these mountains in here that are called nunataks. It's an Inuit word that means, well, it describes a mountain that is never covered by snow, totally, at least, because of this the material that are forming the mountain, or, well, actually the peak, not the real mountain, only the peak of the mountain. All the orientation in relation to the sunlight, many things that makes that these peaks are not covered by snow. And what makes Antarctica similar to Mars? Well, first of all, the temperature. Mars, even if many people think that is warm, it's really cold. It's really cold. You can get minus 150 degrees easily in the equator. I mean, not in the poles, where you can get even less. And also here, the UV radiation in Antarctica, here the UV radiation is higher than in the rest of the planet, and it's similar to the one that we have on Mars surface because of the thin atmosphere that we have on the red planet. And also some places are really dry. I'm going to show you some pictures about it. This is the show-off part of the talk. Here you have me working with my colleague in one of these nunatak peaks, just sampling the soils and rocks from there to try to find microorganisms in there and understand what they do to survive these conditions, what their adaptations are, what are their metabolism. So just to think how they could look like on Mars, for example. Continue with my showing off. Here is me on top of one of the glaciers with another colleague. It is this guy here. And what is interesting about this picture, a part of its beauty, is because we have this drill in here. This is a core taker. So core taker, I don't know if it's a right word in English, sorry. And this is used to take cores from the glacier ice. So what we wanted is just to go deeper and deeper into the ice to try to find some active microorganisms, saying, okay, well, we have ice. We know that we will find cells in here, but are they active or not? That makes a big difference, because as we have learned from the Mars Express mission the other day, is that there you can have thick layers of ice on Mars as well, but they are covered, so they are not going to be in the surface. Would it be possible to have some microorganisms living below the surface or not? That's what we wanted to do with this study. As I said, all these pictures resemble those periods on Mars where you still had some, let's say, restricted water, liquid water in some places, or you have the planet covered with ice. But what about the actual situation, the situation nowadays? Well, there are other places in Antarctica that are also very cold and very dry, as Mars is now. And they are cold. One of the best examples is the dry valleys in McMurdo, where one of the biggest, if not the biggest, station from the States, research station ruled by the United States, is here in Antarctica. And then you have an example of different valleys in here. What makes these valleys so interesting? For some people, they are considered the best terrestrial analog of Mars that we can find. Well, the thing is that the situation that they have, as you see, this is our meters above sea level. They are really, 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 really high. It's 140, 1200 here, 1800. Even this mountain ridge here is 2600. You see that they are devoid of ice, while the rest of the surrounding areas are covered by ice. Well, the thing is that because of being so high, because of being so cold, the mean temperature during the year gets to minus 50 degrees Celsius. You see that there's nothing in here, and it's because you don't get liquid water in there. This is the one image from one of these dry valleys in here. So they follow their name. So for you to have an idea of how difficult it is to find liquid water in here, I can say that you only have, if you sum all the periods where liquid water is possible to be present in this area during the year, like seconds, minutes, all together, you will only have 72 hours of liquid water during the year in here. That means three days during a year of liquid water, but not continuously, not one in a row, 3 days in a row, just minute. Maybe in 2 months you will have 2 minutes of liquid water. So imagine how difficult it is for living organisms to live in here. Actually, if you have in mind an actual image from Mars, you will find some similarities between them. So going back to this place, where can microorganisms live in this place? I tell you, there are living organisms in there, but they are looking for shelter. So where can you go if you want to be covered, if you want to be safer than in the surface of this inhospitable area? You go into the rocks, and that's what they do. Here you have an example of a rock from one of these places. Here you see this is the top part of the rock, the one that will be in the surface. This part is going to be, well, it's the one that is close to the ground. And then you see after, below the surface, a few millimeters below the surface, you have this green layer. This green layer is formed by microorganisms, photosynthetic microorganisms. Why they live here? Well, for some reasons that are really important. First, they are covered by this translucent layer, so the UV radiation will be much less, a few millimeters below the surface than in the surface. So check, we have one layer covering us from the harmful UV radiation. Second, temperature changes in here are much milder than the ones that you have on the surface of the dry valleys or Mars. And third, the special structure of this is a sandstone. As you see, there are a lot of sand grains here, allows water to be captured inside of these rocks. So even when we have only 72 hours of liquid water during the year, these rocks can just get the water inside them. So microorganisms will have a much more milder environment in here, so they can thrive. And that's what they do. You can find life everywhere. That's something that I'd also tell to other people who attend to my talks or my classes, is that the difficult thing is just to find somewhere on Earth that is devoid of life. Normally, you will always find life. So this is another strategy. Find shelter for microorganisms to survive. If we have the same conditions on Mars, maybe we are not looking enough into rocks to find these microorganisms living there. And with these kind of rocks, we also performed an interesting study. This is the experimental setting that we used. What we have here on the left is a Mars chamber simulation called MARTE. It's here in Madrid in the Astrobiology Center that I told you, Centro de Astrobiología, and it's a Mars simulation chamber. So what we did is just to place our rock samples inside and make them live under Martian conditions for, let's say, 3 days, but continuously. So after making the numbers, we found out that we were able to detect living microorganisms and part of these microorganisms in here after the equivalent of 276 Martian years. So it's not so difficult if life have ever appeared on Mars, and you have it sheltered somehow on the surface of Mars. It's not going to be that difficult. I mean, it's going to be difficult. It's going to be very difficult, but it's not going to be impossible to find biomarkers of life. I mean, at least parts of this microorganism that have lived there. So yeah, sheltering is a good strategy. Looking for something to cover you, to maintain the temperature, to maintain the humidity in habitable levels. It's a good strategy for microorganisms to thrive. Actually, that's what they do. Here, I show you another study that we carried out in 2021. This is in a place in the States, in Northern California, called the Lava Beds National Monument. And what we see here is a cave, and this that seems to be water is actually water ice. And what we did was just sample these places in here to try to find these active microorganisms. And yay, we found some active microorganisms. So another idea of where life can be hiding on Mars: caves. If we know that we have ice below the surface, if we know that there are caves because it has a volcanic past, so probably we'll have caves like this, lava caves, and we have ice on them, and it is sheltered, and with all the things that sheltering means for life, why is not going to be possible to find life there? We found life, active life, in these caves. So, well, maybe it's a matter of where we are looking for, where we are looking at. We're looking at the surface, but we need, to go deeper. Never said before, deeper on Mars, right? So apart from these interesting places, I will also want to show you some other places where I have worked. This is Rio Tinto. This is in Spain, southern Spain, so much closer to me than the other places that I have shown you before. This is a really interesting place. Probably you may have heard of it before. This is the actual water of the river. It's red. It's red because it has a very high, extremely high concentration of oxidized iron, and then you have these rocks in here, and also the acidity of the water is really high. Comparing it to Martian surface, the iron will be similar to what we have in Mars, sorry. And it probably resembles how the rivers will have looked like when we had water on Mars. The acidity also prevents a lot of organisms to thrive in here, but even if it's harmful for most of the organisms, we can find microorganisms living here and being happy in these waters. Another example of a place that I have worked in, the Atacama Desert. Again, if you look at it, it will remind you of Mars. I mean, this Martian surface is really similar to the Atacama Desert. What's good about this analog when talking about Mars? It's also very dry. As you know, Atacama Desert is the driest. It's hyper-arid. I mean, it's extremely dry, and it's also the oldest desert on Earth. So these dry conditions has been in place for many, many, many years, many millions of years probably. So if we try to study the organisms living there, we can understand how they survive these conditions, these hyper-arid conditions, the extremely dryness that happens also on Mars. And I tell you again, there is life in there, in the soils and also in the rocks, in a similar way as the one that I showed you before from Antarctica. Again, we have the same picture, so it resembles to Mars. And if we move farther north, we will find the Canadian High Arctic. This is a place called Lost Hammer. I don't know if you have ever heard of it. It's in the Nunavut territory. And what is great about this is this liquid water that we have here. This photo was taken in summer, but we know that this liquid water is still liquid during the winter. It means that with temperatures of -50 Celsius, you will still find this water liquid. Why? Because it has a huge amount of salts, and also sulfur and also other metals. Is a really extreme place. Well, with these conditions, we have found out that there's an active community in there, ruled by, let's say, something that is not very common, that it's anaerobic microorganisms. They are not shown in here, but most of the groups that are present there and active there are working with methane cycle, as you have here, related to the sulfur that is in the water, for example. Something really similar to the things that we can have on Mars, or we know that they were present on Mars. You have probably heard about the mystery of methane on Mars. Well, could it be created by microorganisms? We don't know. But what we can say is that if there's this methane on the surface of Mars, probably you will have microorganisms that could use this methane to survive. Well, and just looking at it again, the cool thing about this is that if you have a closer look to it, it doesn't only look like the surface of Mars, probably in the poles, but it looks like other satellites in our solar system, for example, Europa. This is an image from Europa where you see the ice. You know that Europa is a moon of Jupiter that is a ball of ice. And what we have in Europa, and what is interesting about Europa, is that even if it's outside the habitable zone of the solar system, it could be habitable for microorganisms. Why? Because under the surface, below the surface that we have on Europa, what we have is an ocean of liquid water. Here is a representation of what we may have. We have this cover of ice, then we have this liquid water below the surface, heated by volcanic activity. And why we know that? Because there are some fractures in the surface. These darker areas here probably are coming from a fracture that allows, in the way of a geyser, the water to come out from the oceans and be spread in the surface of Europa. So what's good, what's nice, what's great about the oceans below this ice of Europa is because we will have a heating system that will heat the water enough to be in between the margins in the thresholds of living organisms, the living organisms that we know that may need to be able to develop. And it's also covered from the radiation that comes from the outer space. So if we have these components, these elements, this is a really interesting place to look for life. And it's not the only one that we have on the solar system, because Enceladus, that it's another moon that has the image is not so good, but you can imagine how it looks like. It's the same. Enceladus is another icy moon. It's called icy moons, where you have this cover of ice and an ocean below it. So all these fractures probably are throwing up to displace this water coming from the inner ocean. Another place where we can find life, we are expecting, we are hoping, let's say, better than expecting, we are hoping to find life in the future, is also Titan. Titan is not an icy moon, but it's also a moon where you can have liquid elements in there. Most of the liquid lakes, the liquid elements that are on the Titan lakes or oceans are hydrocarbons. A hydrocarbon is an organic compound, so we know that there are some microorganisms on Earth that can eat these hydrocarbons. That means obtain organic matter and energy from them. So if we have that, if we have methane, and we know about the methanotrophs that we have here on Earth, why is not possible to have these or similar to these microorganisms in Titan as well? Well, that's something to think about, because Titan also has this atmosphere, has all the habitable things that are needed for life to develop. And well, that's almost the ending of my talk. Yes, this is the last showing off images that I want to show you. This is me working in the Canadian High Arctic, in the area that you can see behind me. Is the same place. Is this peak here called Wolf Peak. Well, that's it. That's what my work is. I hope that you have learned some interesting things. And I hope that you enjoyed the talk. And if you have any questions, this is the time to ask them. Thanks for your attention.
Thank you so much, Miguel. That was incredible. As you can see, Vivian and I are on theme with some of our worlds here. And as some of you in the chat know, water bear don't care. Water bear can survive anywhere. So we did have some questions in the chat, but we are running just at the top of the hour. So I am just going to ask two questions that came in from the chat. How different is the atmosphere on Mars from the South Pole where your study took place?
How different is the atmosphere from Earth to the one on Mars? Is that the question?
From the South, the area in the South Pole where your work took place versus the Mars atmosphere.
Yeah, well, the atmosphere actually is really different in Mars than the one that we have on Earth. First thing that makes the difference is that the atmosphere on Earth is much thicker than the one that we have on Mars. So this means that together with different conditions about the planet, like the size that makes the gravity to be less, makes all the elements, for example, water, to be easy to go out the planet. And also the chemical composition is much different. On Mars, we have a 96% of CO2. So you can think that could be a good thing to have a warm climate because of the greenhouse effect that it can create on the atmosphere. But because it is so thin, it's much less thicker than the one that we have on Earth. It makes that the planet to be so cold. So yeah, it's different in terms of density and it's different in terms of composition. But even with that, microorganisms can live without having, for example, oxygen. That is like the key element on the surface of Earth for organisms like us to thrive. But for microorganisms, it's not a problem. You don't need oxygen. You can use many other things.
Great, thank you. And then we're just going to ask one more question, and we will collect other questions to hopefully have answered down the line. But given the recent sample return from OSIRIS rats, how excited are you at the potential of enzymes and proteins? And
I'm really excited. Well, we have learned a lot of things about the organics on Martian surface. What's the not so cool thing about organics? Or an organic compound is something that forms part of an organism, but it cannot be created only by organisms. So the technical words are even if it's an organic compound, it can be created by abiotic processes. That means that they don't need to have a living organism creating those compounds that we have already found on Martian surface. So the exciting thing about the Mars sample return mission is that we will be able to implement our best analysis, our state-of-the-art instrument that are not able to be part of a payload on a rover, on a lander, because they're really heavy or really difficult to manage. We will have these samples back here and we can experiment with them. So if there was life in Mars, probably this is the best chance that we have to find it and describe it.
That sounds
incredible. At least for now, it's really exciting. It's really exciting. When I heard that it's getting delayed, I was like, oh my God, probably I won't have the time to put my hands into those samples. But hopefully in the future, we'll find out if there's life or not.
Hopefully it's only a short delay.
Yeah, hopefully.
Thank you so much, Dr. Fernández. I'm so sorry to cut the Q&A short, but we are at the top of the hour. But thank you for spending your time with us tonight for Night Sky Network. For our Zoom attendees, Vivian has dropped a survey in the chat And we always appreciate your comments, feedback, suggestions, anything that you want to share with us. We are more than willing to receive. And you can, of course, find this webinar along with past webinars on the Night Sky Network channel on YouTube. And you will join us next month on Wednesday, February 28th, where we will hear from Dr. Marta Simoes for astromycology in space exploration. That is all for this evening. Keep looking up, and we will see you next month. Take care.
Thank you very much.